We will now look at complemented subspaces. If V is a vector space and W is a subspace of V, then in linear algebra we know by extending a basis we can always write V equals W plus Z, direct sum Z. Okay. Now the question is, if W is closed, can we find Z closed as well? So this is the question which we want to say. If yes, we say the closed subspace W is complemented. In V. So the question is whether every closed subspace has a complement or not. Okay. So if W is complemented, then we have V equals W direct sum Z, both of them closed. Then we saw by an application of the open mapping theorem that the projections onto W and Z are continuous. This was done last time when we used the open mapping theorem. So let us take some examples. So the first one, W, a finite dimensional subspace of V. Then W is automatically closed, and we saw as an application of the Hanbanach theorem. So Hanbanach theorem implies that W is complementary. Another example, if W has finite codimension, that is, every algebraic complement has a fixed finite dimension, say D. Then we say W has finite codimension D. Then W is complemented. Why? Because any algebraic complement has finite dimension, so it is automatically closed, and therefore trivially this is an acceptable decomposition. So how do these finite codimension spaces happen? So how do we typically get spaces of finite codimension, subspaces of finite codimension? So let V be Banach, and let us take Z finite dimensional subspace of V star. Let us say dimension Z equals D. Then its annihilator Z perp contained in V has codimension D in V. So this is the typical way in which they occur. Now how do we have this? So we define a map V from V to RD. So let F1 Fd be a basis for Z. Then you define a map from V to Rd, okay, phi, call this phi. So phi x equals F1x Fd of x. Then of course phi is this map is of course continuous, linear, and in fact phi is onto. If it is not onto, then the image of phi is a subspace of V which has of Rd, which has strictly less dimension. Therefore, by the Hanbanach theorem, there exists a continuous linear functional on Rd which is not identically 0 but which vanishes on the image. So, what is a continuous linear functional on Rd? Again, it is just d scalars. Not vanishing means not all constants are 0. So, there exists alpha 1. So, if not alpha d, not all 0, such that it vanishes completely on this image of phi, such that for every x in V, we have sigma I equals 1 to d alpha I fi of x is 0. That is sigma alpha I fi I equals 1 to d is the 0 functional, which is a contradiction since the fi are linear independent. They have taken a basis and therefore these are linearly independent and so. So, since this is onto, I can always find an x such that any given d-dimensional vector I have a solution. Therefore, in particular there exists ei I equals 1 up to d such that fi of ej equals 1 if I equal to j and 0 if I is not equal to j. So, you can always find vectors of this kind. Then it is clear that ei I equals 1 to d are linearly independent and span of E1 to ED. So, this is a d-dimensional subspace. Direct sum Z perp is in fact equal to V. In fact, one can easy to check. Therefore, Z perp is has finite codimension. So, this is how you have subspaces of finite codimension. So, now I am going to make a definition. So, definition VW Banach and T belongs to LVW. So, it is a continuous linear operator which is onto. We say that T admits a right inverse if there exists S belonging to L of WV such that T of S is identity. T composed with S is identity in W. Okay, so so this is called a right inverse. Okay, so it's on the right. So you have this. So you first go from W to V and from V back to W. So that is T composed with S, and that should be identity. So what does it mean? Any Y will be equal to T of S of Y. And therefore every Y will be T of something. So necessarily if you have right inverse, the mapping has to be surjective. Okay. So now we are going to characterize mappings which have right inverses. So proposition. Okay. So V and W Banach and T in LVW onto. So then the following are the equivalent. One, T has a right inverse. Two, N, which is the kernel of T, the set of all x where Tx is equal to 0, is complemented in B. So having a right inverse is equivalent to saying that the subspace N is complemented. N is odd since it's the kernel of a continuous linear mapping, it is automatically closed. Okay, so proof. So we will have first one name place 2. So T has a right inverse. Let S belong to LWV be a right inverse. So you consider the space, consider S of W, which will be contained in V. Okay, I claim that S of W is in fact a complement for N. Okay, so let X belong to N intersection SW. So X belongs to N, so X, T of X is 0. X belongs to S of W, so X equals some T of Y, S of Y. So Tx is T of S of Y, but T composed with S is the identity map, and therefore this is equal to Y, and therefore T of X equal to 0. So Y equal to 0 implies X equal to 0. And therefore we have that N intersection SW is singleton 0. Next, let us take any X in V, X minus S of T of X. Consider this. So if you consider this vector, let us take T of this. So this is equal to Tx minus Ts, which is identity, times Tx, so that is Tx minus Tx, which is 0. Therefore, X minus S of T of X belongs to N, S of T of X belongs to S of W, and therefore every X can be written as a vector in N plus a vector in S of W, and therefore this implies that V equals S of W plus N. And since their intersection is only 0, this is in fact a direct sum. Finally, we have to show S of W is closed. So let Yn be a sequence in W such that S of Yn converges to some X in V. So Yn equals T of S of Yn, and therefore that should converge to T of X. Therefore, X is the limit of S of Yns but S of Yn goes to so this goes to, so Yn goes to T of X, so this goes to S of T of X, and therefore X equals S of T of X, and that belongs to S of W. So S of W is closed. Okay, so this shows the S of W is a closed and it is a complement, algebraically, and therefore it is a topological complement as well. So the kernel is indeed complemented. Okay. Now 2 implies 1. So n complemented in V. So let V equals n direct sum M. Then, so M will be closed, N is already closed, everything's. Then the projection P from V to M is continuous. So let X, so we have to show that there is a right inverse, so we must define the map. So let Y belong to W, then T is onto, so Y equals some T of X. Define S of Y equals P of X. Okay, so we have made a definition. Now this definition depends on the pre-image of Y, namely X, and there can be many because it's a surjective map, so there can be many X's for which this can happen. So if we have X1 and X2 such that Tx1 equals Tx2 equal to Y, then we have X1 minus X2 belongs to N. So P is the projection to the complement, so P of X1 minus X2 equal to 0, therefore P of X1 equals P of X2, and therefore it does not depend, whatever may be the pre-image, the Px is always the same, and therefore this means that S is well defined. Okay, so now let us take T of S of Y. This is what? T of Px. But x minus Px belongs to N, and therefore because Px is a projection to the complement, so x minus Px belongs to N, so Tx is always equal to T of Px. So this is equal to Tx, and that is equal to Y. So T composed with S is the identity in W, and therefore we have found a candidate. So enough, so now to show S is continuous. So let us do it by the closed graph theorem. So we will use the closed graph theorem. We can do it with the open mapping theorem if you like. So let us take Yn converges to Y in W, and S of Yn converges to some X in V, and we have to show Y equals S of X, or rather the Yn converges to Y, S of Yn converges, so to show X equals S of Y. So this is what we need to show. Okay, so let us take Yn must be equal to some Txn. So S of Yn is nothing but P of Xn. Okay, and that converges to X. Remember, since the projection is always in M is closed, so this implies that X also belongs to M. Okay, so in particular you have X equals P of X. Okay, so Yn is also equal to, Yn is T of Xn, which is equal to T of Pxn also, we know. Okay, so Yn equals T of Pxn. Pxn, So now you pass to the limit, Pxn converges to x, Yn converges to y, so y equals t of x. So Sy equals p of x by definition, and px equals x because it is in M, and therefore we have shown that Sy equal to x, and that is exactly what we want, and consequently by the closed graph theorem implies S is continuous. So you see, we have assumed Yn goes to y, Syn goes to x, and then we showed that x equals Sy, so the graph of S is closed, and consequently since we are dealing with Banach spaces, we have been able to show that S is continuous. Okay, so the next thing we will do will be to look at adjoint of an operator, and since with very little extra cost we can do it in a more general setting, so we will take that up next. Okay, thank you.